To perform a measurement of spectral transmittance, the DTR6 should be moved to the left-hand stop of the optical rail. I have placed the reflectance port cover at the reflectance port and the small set of clips at the transmittance port. We can now perform a measurement of the reference level with no sample in place. Now moving to a measurement of spectral transmittance, we must first go to Scan Reference Setup to ensure that the Use Reference Calculation function is not implemented. We will now go to the Scan Setup and define, let's use the same spectral range, 300 to 1200 nanometers, New Scan. Again, in measuring the reference level, the y-axis should always show signal in nanoamps. At the end now of this scan of the transmittance reference level, we will save to file again in the spectra folder the transmittance 100% and today's date, and we will go to Scan Reference Setup to load that measured reference file name, transmission, but there is no calibrated reference associated with it. There is only 100% transmission of light straight through. We need not consider that value then. We select the type, transmission, percentage units, use reference calculation, apply. We return to Scan Setup, and now I will look at the transmission of a sample. So I will now use BEMA Plus to let light be transmitted from the monochromator with a view to placing the sample at the transmittance plane, using the clips to hold the sample in place as best as possible. And once in place, we can now perform the measurement of the spectral transmittance of this particular DSSC sample. And now we hit New Scan to measure the transmittance. I've performed a measurement here over the spectral range 300 to 1200 nanometers, whilst this sample is a dye-sensitized solar cell which does not respond over that range. So to a certain extent I have gone past the spectral range necessary, but for demonstration it is of use. And we have the measurement of the spectral transmittance of this particular sample, showing interesting interference effects at the longer wavelengths, no doubt due to the thin films deposited on the sample. We can use this with the measurement of the reflectance of the device to modify the external quantum efficiency measurement to obtain the internal quantum efficiency.